All right, we are recording, so welcome to today's lecture. I think last week I was incorrect, so this is the third to last week of lecture now. So we have 6 more lectures before it's all over. For those of you who noticed, I have finally posted Homework 8. I was a little bit late about that, so it covers stuff from Chapter 2 and the first 2 sections of Chapter 3. So nothing that we do today is on Homework 8. And it'll be due Sunday night, so hopefully that gives you enough time to finish that. And then we'll have one more homework after that, which I'll probably assign sometime next week. There will not be a reading quiz for Thursday because I've already assigned the reading quiz for sections 3.3 and 3.4, which we're going to be covering today and on Thursday. I've also had a question about projects, so there will be one more project. It'll be a command line calculator for which you'll have to do a push-down automaton, but we haven't learned about push-down automata quite yet. So if you want, I can assign it, but we haven't covered the material yet. But that's your work on it. And the scope of it should be a little bit less than this previous project, or the one that is due tonight, which reminds me, yes, project 2 is due tonight. So please make sure you turn that in. And if you have questions, then there's still office hours after. And I'll keep an eye out on Piazza for stuff throughout the day as well. Okay, so let me share the desktop with you and get the chat window back up. Okay, so last time we kind of started on this whole relationship between DFAs and NFAs. And we then said, well, every language accepted by a DFA is also accepted by an NFA. And that is essentially due to the fact that the transition diagram for DFA is also one for an NFA. So that direction actually makes perfect sense. So if you have a deterministic finite automaton, that kind of also is a subset of a non-deterministic one. So that should be no surprise. But then we talked about epsilon closure a little bit, and that was the last thing we did. But today we're now going to show that every language accepted by a non-deterministic finite automaton is also accepted by a deterministic one. And that is not obvious at all. So essentially, we're going to show that you can always construct a deterministic finite automaton when you are given a non-deterministic one. And there's quite a bit to process here. So we're going to spend a lot of time just on this construction today. So if I just scroll down to kind of go ahead, so this will be the NFA that we're looking at, and it's very simple, right? It only has 3 states and a few transitions. Here's the regular expression that it recognizes, but then the resulting DFA will be something like this. And I don't know if you kind of were able to follow the reading. It's pretty dense, and how we arrive here is not quite obvious at all. So I'll be spending a lot of time just getting here and adding in insult to injury here. It actually turns out that this automaton is actually incorrect. So some of these transitions here, I think this one is incorrect. So there's a few incorrect transitions in this figure that haven't been corrected yet. So that probably, if you even try to follow everything, kind of just added to the confusion. So let's do this properly. And before we do that, let's actually take a look at the rules or the proof. And everything is kind of straightforward. So we need to have a new set of states, which will be the power set of Q. I'll elaborate a little bit earlier. Here's a rule to determine the start. And if I'm going to skip number 3 for now, here's a rule to determine which should be the new accepting states for the deterministic automaton. But then there's this, and this is kind of the beef of everything, but it is a very confusing notation here. So it just says, well, if we are in one of our new states like this, and we have a symbol here, then we're going to define the transition function, which will then tell us which state we're going to enter. And we're going to need to determine this new state R. Sorry. Oh, the sets of states are, it's already getting complicated, for which all this stuff here is true. And this is a very tight mathematical notation, and then the explanation also doesn't clear things up completely, I would say. So we'll need to see how we actually, so it's important that we understand how this transition function needs to work. And essentially, this is not the edges of the automaton. And hopefully, just by doing the example, I will be able to elaborate on this. Because I think it helps tremendously actually looking at a picture while doing all this stuff. So given that essentially we're going to get from here to something like this, I'm not going to do my hand annotating stuff. So it is now time to switch to some software to do this. And for the homework, I'm telling you, you must use this. So, so it's the Finite State Machine Designer. There's a link to the URL in your homework assignment, because I'm actually planning on having you use this for the final exam as well. So it's a website. I think once you've loaded the website, you don't have to be online anymore for it. And if you scroll down, there's a little bit of explanation on how you actually do stuff. So if you just double click like that, then we now have a state. And I can enter its name. So I can say Q. If I use the underscore symbol now, and now hit a number, then it'll automatically subscript stuff. So this will be Q0, and then I can double click again and say this is Q1, for example. Then if I say Q1 should be an accepting state, I just double click, and now it's an accepting state. If I draw an arrow while holding the shift key, and on my laptop that is a little bit awkward, well, that will be until you click in, then that could be the starting state. And now if I move this whole thing, everything connected to it moves around with me. And now I can draw an arrow here like that. And I can label that. So I can say on 1, go this way, for example. And now if I move stuff around, I can move this. If I want to move the edge, I can kind of bow that as much as I want, and it kind of stays bowed. And then I can do a self loop. So by default, it's just that. So on 0, I can do this. And then I could do something like that. And if I, this is now LaTeX notation, it's kind of this backslash. If I just type epsilon, and once it's complete, then it's the symbol epsilon. If I want to change the name, that was not what I wanted. If I want to change the name, I'm going to click on it, and then I can just hit backslash. And like that. And that is pretty much all the functionality we need to draw stuff. If we want to delete stuff, we should select it, and then hit the delete key, and then everything goes away. Not the backspace, the actual delete. And that again is complicated on my MacBook, for example. I actually have to push the function key and the delete key to get rid of that, like that. And then when you have one, you can actually export that as a PNG file. And in Gradescope for an exam, you would then be able to upload that file. So that's kind of why I want you to get familiar with this. And it's also easier for me to do a state diagram and an automaton on here rather than trying to draw it by hand. So the first thing, if we're now back to this. So this is our NFA here. We want to convert that. I'm just going to keep it around at the bottom here. Move that up a little bit, almost. Is that still okay like that? I suppose.
Yep.
All right, so the instructions or the proof now tells us we have three states. We need to build the power set of that. So the power set of Q0, Q1, Q2 is pretty much every possible combination of states involving these three. So clearly we're going to have Q0, we're going to have Q1, and we're going to have Q2, but we're also now going to have combinations. So we should have Q0, Q1. And we need these states because in an NFA, we may be in a position where we say, well, we don't know which state we're going to be in based on our input. So if I put up Q0, Q2, it's a little bit obvious from the start. So right off the start, there's this epsilon transition, for example. So if I'm in Q0, I might as well be in Q2. So this state kind of captures this, well, we could be in state Q0 or in state Q2 in the NFA, but we need to somehow capture that in the DFA. So that's why we need this power set. So we also need Q1, Q2, oops, like that. And we need Q0, Q1, Q2. That's a state where, well, we don't know, we could be in any of these three states. And since it's the power set, we also need one that it's the empty set. We are in none of the states before. And this one here is necessary. That's kind of our error state, right? We in the NFA, for example, if you look at Q1, there's no transition on 0 here. And if we now are in Q1 and we see a 0, then we just say, okay, that didn't accept it. But the DFA needs transitions for everything. So that's why we would then have a transition from Q1 to this empty set state, because there just needs to be a transition. So this is kind of the error state. When we know we're not going to accept it, we're just going to transition in here. So these are our new states. And so let's do the start state first. So in the NFA, the start state is Q0. So it's denoted by this. And essentially, Q0 has to be part of the start state for the DFA, but there can be only one start state. But we see this epsilon transition here. So if we start in Q0, we could immediately also be in Q2. So because of that, when we have an NFA, we need to look at the epsilon closure of the start state. And that'll be the state, that'll be the start state in the DFA. So I think this question was on the reading quiz, what's the epsilon closure of Q0 in this graph? And it is just Q0 and Q2. And because of that, this state here will have to be our new start state. So let's do that. Okay, so that was easy. accepting states. So again, I'm going to skip rule number 3 because it's complicated. But let's determine what the accepting states of this DFA are. And the rules state, well, whenever you have as part of the state's name a state that is an accepting state in the NFA, then it's going to be an accepting state in the DFA as well. So clearly Q0 and Q2 by themselves, they need to be accepting states. But now every state that has a Q0 or a Q2 in it also needs to be. So this one because Q0 is in there, this one because Q0 is in there, this one because Q2 is in there, and this one because both of them are in there. So we have lots of accepting states in the DFA. Okay, so now let's go back to this. So we now need to see, okay, we are looking at one of the new states. So we're going to be in one of these states. And we now have to see on A, that's our input. So in our case, that's 0 or 1. How do we need to transition? And we're building a set here. So it's kind of this set of R's here for which there exists a transition in the original NFA. So what does that mean? So let's do these first. So these are a little bit more straightforward because we only have one NFA state represented in these. So if you look at Q0, we would then look at, we are in Q0 in the NFA. And if we see a transition of 0, we go to Q1. So far, nothing really has changed. Okay, I didn't do that quite right. Okay, now. So on a 0, we transition. Oh, that was the wrong direction. Still not right. My apologies. So as before, we transition to Q1 from here. We also need a transition from 1, but there is no transition from a 1 here. So that's why we need to transition on a 1 to this empty state, or the empty set state, whatever you want to call it, like that. And that is because essentially this set that we're defining here will be empty. There are no such transitions that exist. So more interestingly, though, are the ones where we have multiple things going on. So if you look at Q0, Q1, so how do we determine the transition for that? Well, we have to look at both Q1 and Q0. So, and then the epsilon closure also matters. So, so if we were, let's say we're going to observe a 0. So if you observe a 0, then essentially we need to check, okay, that would lead us to Q1 in this. But we could also first do an epsilon transition here and end up in Q. Actually, okay, I did this morning and I was getting confused. So let me just try to remember if the epsilon closure here matters or not. I don't think it does. It becomes relevant at the end. So I might have picked a bad example, but let's stick with it. So if we are in Q0, on a 0, we get to Q1. If we are in Q1, there is no transition to a different state. So on a 0, we transition to Q1 in this case. If we are in Q0, there is no transition that is labeled with a 1. So we always have to then look at both states, or all the states that are represented here. If we are in Q1, however, there is a 1 transition to Q0. But now the epsilon closure actually comes into play. So we can't just say on 1 we're going to go to Q0, because we could immediately go on to Q2. So we don't know whether we would end up in Q1, in Q0 or in Q2. And that is exactly what this state is representing. So on a 1, we would go here. So at this point, I just want to check if everybody is still with me on why we are going here. Did that make sense? So again, we're looking at both states. We're looking for 1 transitions. There's none going out of here. There's 1 going out of here. And then because of this epsilon transition, we have to enter this new state, because we could be either in Q0 or Q1 after this 1 transition. So the double and triple states. So they are there because of these epsilon transitions, essentially. So in an NFA, we can just say, we're at Q0, but at any time, without consuming an input symbol, we can just switch to this state. And because of this, we kind of built this power set that kind of said, okay, we could be in these 2 states simultaneously, and then look at our input, or in these 3 states simultaneously, which in a non-deterministic automata is just, well, yeah, you can do whatever you want. But in a deterministic one, well, we need determinism. So we kind of have to capture the possibility that, well, the NFA is currently either in state Q0 or Q2, and we just make this DFA state that kind of captures that information. So now we have to continue this. So if we looked at Q2, for example, Q2 is just going to have on 0 a self loop like that. And there is no transition from 1, so we're going to have to transition here like that. And that's the nice thing. We can now just shift some stuff around to make it a little bit nicer. Q1, let's take a look at Q1. So if you are in Q1, then there is no 0 transition. So on 0, we would go over here. We'll clean this up a little better. And on a 1, we would go to Q0, but we need to take the epsilon closure of Q0 as the resulting state. So again, we would be going here on 0. So just 3 more to go, yay. So let's do this one. So if we are in either of these states, then on a 0 transition, Q1 would go to Q0 would go to Q1, but Q2 would stay in Q2. So on a 0, we could end up in Q1 or in Q2, which is why we need to transition to this state. On the 1, there is no transition with the 1 out of either of these two states. So again, we will go here. So if you look at this one, so we're in either of these two states. So on a 0, we would just have the transition from Q2 to itself, and there's no transition on a 0 out of Q1. Oops, that was. So we need to go to Q2 from here, like that, on a 0. And we can kind of drag these down a little bit, like that. And if you are here now on a 1, there's no transition out of Q2, but there's a transition here to Q0. And again, we need to take the epsilon closure. So on a 1, we would go to Q0, Q2. So we would go this way. And that looks awkward, so we can kind of pry these apart a little bit, like that. And we're almost done. And then there's probably questions you have. But let me just finish this one. So now we need to regard all 3 states and see, where do we go on a 0? Well, we have a 0 transition here to Q1 and 1 to Q2. So we would again go to this state, like that. And on a 1, we would just transition to Q0 and take the epsilon closure here. Oh, sorry. This one was on a 0, we go to Q1 and Q2. So we should have gone to that one. Can I modify that? Nope. So let me delete. All right, so because we have a transition to Q1 and to Q2, we need to end up here. And on a 1, we transition to Q0, but need to take the epsilon closure. So we are going this way on a 1. Okay, I need to find that. I suppose. And that is the resulting, no, haven't done this one yet. So this one is pretty straightforward. Here we just need, because there is no state empty thing, we would just stay in this state on any input. So we need this self loop here. So this is now the resulting DFA from this NFA, and I know it's ugly. But if you now kind of trace this a little bit, so we said this NFA was alternating 0s and 1s, right? You have a 0, you come back with a 1, and then followed by an arbitrary amount of 0s. So that was kind of what is being accepted here. So we need to do the same thing here. So in order for us to accept a string here, it has to start with a 0, or it can be completely empty. So completely empty works because start state is an accepting state, just like here. But now if you have a 0, we transition here. And if you now see a 1 again, we go back here. And if you see a 0, so we have this alternating, that's kind of the interaction that used to be here, we were now seeing between these two states. And if we see a 1, then we enter this error state, because when we are here, we don't want to see any 1s. So if you see a 0 now, then this whole Q, we could be in Q1 or Q2 here as well. Then we need to make this an accepting state, because just a single 0 is sufficient for this to be accepted. But we could then say, well, if you see another 0 now, then we're done with seeing 1s, and then we can see an arbitrary amount of 0s anymore. So if you compare that to this, then depending on how I rearrange these, well, good, I got this at the bottom, Q2. Guess that's just a, yeah, I guess I'm pretty close, except that these two are switched, I guess. Oh yeah, and that's because, all right, so this is better because, so a bunch of these transitions were incorrect in this graph. So if you look at Q0, Q1 on 0, we are going to Q1. I'm just trying to find out. So I think some of these empty. So Q1, yeah, so on, no. See, when I did the example, oh, maybe it was just, maybe these are just not relabeled correctly in the. All right, so if you look at Q0, then it said on 0, we transition to this empty state, and on 1, we transition to Q1, but it needs to be 0 and 1. So the labels were incorrect there, and something else is incorrect as well. However, all right, question in the chat first. So if Q1, Q2 means you're in either of those states, then why is it valid to get a 1 from there? Would cause an error if you were actually in Q2. Yes, but you could be in Q1, and therefore we are allowing this transition here, but these are only the transitions you would have taken from Q1, right? You would be able to go to Q0 and Q2 from there. So it's not actually being simultaneously in both states. I'm just trying to remember. See, I never actually bothered teaching the proof, because I think just the conversion is enough for you guys to take in. So essentially it says, yes, you could be in these two states, but you kind of get to pick. So if you are here and you see a 1, then you have to go back here, but you're also allowing the transition from the 0 into the Q2. So it's kind of you're in both at the same time. Okay, I'm not sure if I completely explained that well. But when I explained the actual string, we kind of only focused on some subset of these states here, right? So it turns out that some of these states are completely unreachable. So there's no error actually going into Q0 or into this one. So that really means that we can simplify this. So I don't need this state. So once I'm done with this, I can just say, okay, let's get rid of that one. And this one doesn't have any arrows going in. let's get rid of that one. Now this one doesn't have any going in. So this was a state that had one coming in, but it was from a state that wasn't reachable. So that one can go. And finally, this one can go. And now I'm left with just this. And that now actually looks exactly like this. So, all right, good. I didn't screw it up. So these rules are a little bit complicated as to how to draw these arrows. Plus, it's also a lot to kind of do this power set. So there's actually a more straightforward way to do this. Because if you kind of continue on, so this DFA that recognizes the language of the NFA in figure 3, well, let's take a look at figure 3. It's all the way up here somewhere. Here it is. So this is the NFA from figure 3, and we note that it has 6 states. So what's the power set of that? Well, it's 2 to the 6th power, which is 64. So we don't want to draw 64 states and then realize, oh, turns out we only needed 1, 2, 3, 4, 5 out of these 64. So how do we get here without doing the 64? Well, let's first do this example again. And the key lies in, so let me delete everything. So the key lies in not drawing states that we can never reach. So, so we should start with the start state. So we first should see, okay, what's the epsilon closure of Q0? Okay, it's this. And now go from here. So we now need to see which states do we reach on a 0 transition. Well, on a 0 transition, we can reach Q1 from Q0, and from Q2, we can reach Q2. So we should now, I think it went down here, but say, okay, we can reach this state through a 0 transition. And because Q2 is an accepting state, this needs to be an accepting state. We now need to see, okay, on a 1 from Q0, Q2, well, there's no transition with the 1 going out of Q0. There's no transition going out of Q2, so we need the empty set state. And on a 1, we need to go there. And might as well do that now. Empty set state always has the self loop with all input symbols on it. So now we've done this state. We're done with the transitions from this. We're also done with the outgoing transitions for this. So we now need to look at Q1 and Q2. So 0 transitions out of here. There's no 0 transition from Q1, and there is one from Q2 into Q2. So we now need to have state Q2 because it's reachable. It is an accepting state. And we reach it from here. And that was on 0. We're still doing the transitions for this. So on a 1, we can go from Q1 to Q0. And we need to take the epsilon. So technically, we always need to do the epsilon closure. I'll only mention it when there's actually an epsilon transition that we actually need to do the epsilon closure. So you can reach Q0 and Q2 on a 1 from this state. So that was that. So now we're done with this. So now we need to look at Q2. So Q2 on 0 just stays in Q2. And there is no transition on a 1. So we need to transit like this. And now we're done because these were all the states. So we essentially have all the transitions from all the states and nothing of the other stuff. So we didn't have to draw any of this unreachable stuff. And that should be, hopefully, again, exactly the same thing as before. Yes. All right, questions about this example? All right, so it's a little bit awkward. You kind of have to delete everything by hand. If you just delete nodes, then everything will go away. All right, so because I think we need another example, but I haven't done this ahead of time, but let's take a look at what is going on here. So if you want to convert this into a DFA, yeah, gonna be good enough. What's our start state gonna be? Q0. So if you look at the NFA, then the start state is Q0 here. So then we need to now look, are there any epsilon transitions out of here? And I'm not seeing any. So indeed, Q0 is our start state, like that. It is also an accepting state because it is one in the NFA. Okay, awesome. So on 0 from Q2, where can I end up? What if a start state has multiple epsilon transitions? Then all of those states that can be reachable through epsilon transitions must be combined. So if there were an epsilon transition here and here, let's pretend these weren't ones, but epsilons, then the start state would be Q0, Q1, Q2. So one state called Q0, Q1, Q2. And even if this were a 1 and only this were an epsilon, then because we could go here for an epsilon and then here through this epsilon, it would still be this meta state Q0, Q1, Q2. So we are in Q2, that's our start state. Now we can accept 0, 1 with 2 options when receiving a 1. Yes, so, well, accept or transition, those are different things. So let's take a look where we can go with a 0. So when we're in Q0 in the NFA, on a 0, we just stay in Q0, and that's it. So we do need the self loop here. Okay. There we go, like that. And that's all that's going to happen. Okay, on the 1 though, it's going to be more interesting now. So on a single 1, we can end up in Q1 as well as in Q2. And we also need to be aware of epsilon transitions. So we could go this way and do an epsilon here, or we could go this way. So either way, the new state that we're ending up with is going to be Q1, Q2. Like that. So on a 1, I'm doing this. This is not an accepting state because neither Q1 or Q2 are accepting states. So now we have to kind of broaden stuff. So on a 0 here, we can go to Q1 from Q1, and there's no 0 transition out of Q2. So we now need state Q1. And on a 0, we are definitely going here. So on a 1, we can go from Q1 to Q3, and from Q2, we can also go to Q3. Like that. Also not an accepting state. All right, let's do Q1. So Q1 on a 0 just stays in Q1. And on a 1, oh, I screwed it up. So I screwed this part up. So can anybody tell me what I screwed up? So I said on Q1, Q2, if I'm in this state, on a 0, I stay in Q1. What did I forget to consider? Yeah, I forgot about this epsilon transition here, and I always have to take the epsilon closure of the state I'm arriving at. So if I'm arriving at Q1 on a 0, I'm really, oops. Oh. Staying here. All right, so let's make sure that the Q3 part was correct. So on a 1, I go to Q3 here, and I go to Q3 here. There is no epsilon out of here. All right. So my apologies. That's what happens when you don't prepare stuff. But I was actually hoping to not make any mistakes. But you can see it's tricky. You would not be getting a graph like this on an exam because it's already way too complicated. All right, we are now at Q3. And we now have the possibility on a 0 to stay in Q3 or go to Q5. And neither of them have any epsilon transitions. But we now need a new state, Q3, 5. And on a 0, that's where we're going to go. If I'm here and am on a 1, then I'm only seeing one transition to Q0. And there is no epsilon out of here. So on a 1, go this way. All right, so next state to consider. I did forget one. Thank you. All right, so that's that one and that one. So we are not going this way. We need a new state, Q0, Q4. And that will now be an accepting state because it contains Q0. And that is where we go on a 1. Thank you. Oh, and that has an epsilon, but it goes to Q0. So we're still good with that. All right, Q3, Q5. On a 0, I can stay in Q3 and from Q5 go to Q3. So on a 0, I'm just going back here. Epsilon is a whenever you like it transition. So at any given point, even in between consuming symbols, you could take an epsilon transition. That's what makes these NFAs really complicated to understand, but rather easy to design, because you can just say, oh, well, whenever we like, we can go this way. It'll come in handy when we build automata from regular expressions in the next section. So we were here and on a 1. So on a 1, again, we can do the Q0, Q4 from here. And there is not a transition on 1 for Q5. So this one too would have this 1 transition here. Like that. So then we need to consider this state. So on Q4 or Q0, so there's a self loop here to Q0, so we can reach Q0 from this state. And there's no 0 transition from Q4. So Q0 is the only state we can reach from either of these 2 states. So I need to make double sure now that. And now we need to look at 1 transitions. So I can go to Q2 and Q1 and Q2. So that will be this on a 1. And I think we now have outgoing transitions for every state. And that might be the final DFA. Let's check. It's similar, but there's a difference here. So I'm saying we're going back this way. Notes say we're staying in the state. So we'll have to come back to that. It could be another mistake in the notes too, or I might have made a mistake. So let's actually arrange stuff the way it's displayed here, just for easier comparison. Yeah, for the most part, it looks like, so with this exception. So let's investigate that. See what actually needs to happen. So when we're in state Q3, Q5, and we're observing a 0, yes. So I made a mistake. So from Q3 on a 0, we can get to Q5. From Q5, when we see a 0, we get to Q3. So when we're in this state and we're seeing a 0, then indeed we would have this. And that now looks the same. So a little bit more complicated, but maybe you're kind of getting a feel for at least how to build these things. Yes? And then you can always try, if you know what it's supposed to represent, you can always then verify, do the languages that are accepted kind of, are they the same thing or not? It'd be hard to catch mistakes like, okay, I shouldn't have gone back here, I should have done the self loop. So one really has to be very careful, and you probably want to double check everything. So questions? All right, double states. All right, so why do we have this self loop here? Come on. All right, so let's say we are in this Q3, Q5 states. So that means in the NFA, we now need to look, okay, on Q3, which is one of the two states here, on a 0, I can go to Q5, and ooh, there's also this self loop, or I can stay in Q3. And from Q5, we just can go to Q3. But either way, from any of these states here, I can reach Q3 or Q5, and therefore we stay in the same state. So even if this self loop here weren't there, just because, yeah, but Q5 is represented here. So from Q3, I can go to Q5. So Q5 needs to be part of my target state. And from Q5, I can get to Q3. So Q3 needs to be in my target state. And from Q3, I can go to Q3. So Q3 needs to be in my target state. So Q3 and Q5 are my target. And my source was either Q3 and Q5, if that helps you. Did that make it better? Worse? So from Q5, you can reach Q5. Well, not in a single transition, but even if there were a self loop here, just because you can go to both 3 and 5, you have to be here. And here we don't even have a Q5 state. Why are you asking why there isn't a self loop here? Because, I mean, that wasn't part of the original NFA.
Yeah, I guess the way I kind of read that Q3, Q5 target state with
No,
the
this does
self
not
loops.
mean that there exists a way from Q5 to reach Q5 itself. No.
Okay. Yeah, I think that's
So
what's
it's
throwing
kind
me
of
off
you're
because
in
when
this meta state,
yeah.
and you kind of in both simultaneously, and you then have to see, okay, which states can I reach from this? So that does not imply that you can, that you were able to go from Q5 to Q5 in the original NFA, so that doesn't matter. So it's really just, okay, I've got these two states on 0. Which other states can I reach from these original states? And you just keep collecting, and it turned out it was Q3 and Q5 again, and therefore we had the self loop.
Okay, yeah, that does clear it up a little bit. I'm just gonna let it marinate a little bit.
Okay. And some small examples you can do yourselves might help kind of getting the feel for it. Since I've done this twice now, I actually feel confident I could do it again on a more complicated example, which I'm not going to, because I would like to at least move on a little bit into the next section. So I just wanted to explain then how to do this. And then I'll probably assign one of these guys for you for a homework. One, not more. So we can always convert an NFA to a DFA, and that means that essentially they just describe the same set of languages, right? They're equivalent, and that's a little bit surprising because you would have thought that an NFA with all the relaxed rules would be more powerful than a DFA, but it turns out it really is not. So it's the same languages that are being recognized by them. So that kind of brings us now to the relationship between automata and regular expressions. So there's this theorem here that says a language is regular if and only if it is accepted by a finite automaton. So it doesn't matter if it's deterministic or non-deterministic. We've just established that. But this now states that essentially, if you have a regular expression, you can build an automaton that accepts that language. And it also states that if you have an automaton, then you can build a regular expression from it. So the proof of this is kind of split up into two parts. So the first one then says, we can build an automaton if we have a regular expression. So, and then later it then says, well, if we have an automaton, we can build a regular expression from that. So I just want to start at least motivating this first part, or going, it's the actual proof actually. So the proof kind of gives us the building blocks of building an automaton. So if I give you a regular expression, then how do I get an automaton from that accepts the language represented by the regular expression? So the nice thing is we can now have little building blocks of automata, just like we had building blocks of regular expressions. So we start then by just saying, okay, these are the elementary automata. So if it's the empty language, then our automaton, okay, let me just delete all that stuff. So our automaton then just looks like this, right? It's got a single state. That's the start state. It's not accepting, so it doesn't accept anything. That's kind of the simplest automaton we can have here. And that is this, a single initial state that is not final. So if R is epsilon, then we just have this. So now it's an accepting automaton, so we accept the empty string, so to speak. So that's our next small building block. And then if it's an element of the alphabet, then we need two states. Oops. And this would be an automaton that accepts a single symbol from the alphabet. So we have an initial state, and only on A we transition to this accepting state. And those were kind of the basic building blocks of regular expressions, right? We had the empty, and then the epsilon, and then A. And then we had operations. So we had concatenation, and we had union, and we had the clean closure. So let's see if we can now kind of have a rule for combining automata. So if we have a regular expression that is the concatenation of two other regular expressions, right? So this states that the regular expression R is the regular expression S concatenated with the regular expression T. So that means we have some automaton MS that accepts or that represents the regular expression S. So something like this. So this is just pseudocode, meaning there's some sort of start state here, and there's a certain number of accepting states. And we have one for T. So how could we build an automaton that accepts S concatenated with T if we have these two automaton that already exist? Anybody want to take a guess? Technically, you could just look at the notes. So there's a reason why I'm not scrolling down. Well, essentially, if I start here, right, S comes first. So I start here, I do my thing. I'm going to end up in one of these two accepting states if the string actually is part of the language. But now I then need to then go on, and I need to process T. So what I need to do is I need to make these two or however many states there are in MS to be non-accepting, and I then need to transition from them to the start state of MT, and these need to be epsilon transitions. So it's easier to do an NFA for this. It's much more complicated trying to build a DFA that combines these, but we saw we can always convert an NFA to a DFA. So the procedure should always be to do this with these epsilon transitions. And if you really need a DFA, then, well, then by all means convert it from the NFA. So, and then we kind of need to make these no longer be start state, accepting states, because we only want to accept these now. So hopefully, I should have cleared that. Okay, clear. And this is kind of what's denoted by this, right? So these are no longer accepting states, and we just add epsilon transitions. And this now is an automaton that accepts the concatenation of S and T language. Yay. And similarly, if you want to do plus, so concatenation really meant S first, then T. Plus just means either or. So what do I need to do for that? Well, I need to introduce an initial new start state. And then if I just have epsilon transitions here, then it's essentially the NFA's choice. Okay, I could go here or here, and then end up either accepting S or T. So this automaton accepts both, accepts the union of the two languages. It accepts all languages from S, and it accepts all strings that are part of the language of S, and it accepts all strings that are part of the language of T. And finally, but a little bit more complicated, the clean closure. So, so for the clean closure, if you look at MS, then it means 0 or more repetitions of S. So if this is our original start state, then I need to, from the accepting states, just have these epsilon transitions back to the start. So that once we've accepted one string, we can then go back to the start and try to accept it more than one time. But the clean closure also says 0 or more repetitions. So we kind of need to introduce this new start state here that needs to be an accepting state for the 0 repetition. So we could just be here with the empty string, or we could continue here with an epsilon transition to the original start state of MS. So do you have any questions about these building blocks? All right, so now if we had a regular expression like this, how do we actually build an NFA for that? Well, the order in which you do stuff doesn't necessarily matter. So you could do the B first and concatenate stuff, but let's just go in sequence. So if I just start with A, then we already have the automaton for it. So then I could do an A plus B. So let's do that. So for A plus B, we need an initial state. And then oops. I'm not having success clicking right now. There we go. So that's the start state. And then, all right, so this is, didn't that happen last time too? Might be just a weekly thing now, or I should just update. Which I probably should, but I don't want to. So if this is the one that accepts A, and this is the one that accepts B, then A plus B, I needed this initial state here, and then I needed epsilon transitions like that. So this whole thing now accepts A plus B. So now we have a clean closure though. So that's the star here. So it's getting a little complicated. So if you just follow the scheme by the letter, then we now need transitions from this start state back here, like that. And like that. But now, and it's kind of redundant, but if you really follow the letters to the book, so that's just this part right now that I've done. I now need to introduce this new starting state that is an accepting. Oh yeah, because that was an accepting state. So that needs to be an accepting state. That is my new starting state. This needs to go. And this needs to be the epsilon closure. So this is now A plus B star. And for concatenation, we just said we're going to combine these. So if I concatenate, and I'm no longer making this an accepting state. And you can see it really is redundant. Technically, I could just have the transition from here on A to here and be this and have this to be an accepting state. That would work. But if you really follow the construction stuff to the book, and then what we need to do, we still need to concatenate B here. So we now need to let's move that. So on B, like that, and like that. And I need to do one more thing because this isn't quite right yet. So I need to do all this, the final states. And this one here was an accepting state. Oops. For this whole thing. So I kind of need this transition here going to here. Sorry. On epsilon. And these no longer are accepting states. See, A, epsilon, that one, going here. Yeah, that's pretty much exactly what we have here. So it's pretty straightforward, but we've got a lot of epsilon stuff that technically is like all, like these three nodes here, they could be coalesced into a single node, for example. That's all possible. But that's how we build an NFA from a regular expression. Do we have questions about that? All right, so next time we'll do the much more complicated, let's build a regular expression from an automaton. And then we'll probably start in the grammar chapter 4 as well. Okay, do you have questions about anything? So then we'll just end the lecture. Sorry, I went 4 minutes over. Question?
Could you just go back to the diagram for just a second? The NFA you just made.
Yes.
All right.
Do you have a question?
No, I was just about to finish drawing it.
Oh, okay. Well, there's going to be a video too of it.
Oh yeah, never mind. All right, you're off the clock then.
All right. Any other questions? All right. I'll stop recording at this point.